In this video, we're going to look at a few more examples of the absolute convergence test. Test the following series for convergence or divergence. Question A, summation n equals 1 to infinity, sine n times square root of n squared plus 1 divided by n cubed minus n plus 2. Question B, summation n equals 1 to infinity minus 1 to the power of n divided by log of n plus 1. Let's look at question A first. We have summation n equals 1 to infinity sine n times square root of n squared plus 1 divided by n cubed minus n plus 2. This series has both positive and negative terms because if we look at sine n, we know that sine 1 is positive. If we put this into a calculator, sine of 1 radians, always be in the radian mode, always use radian mode when you're calculating the values of these trig functions. Sine 2, sine of 2 radians is positive. Sine 3 is also positive, but sine 4 is negative. But it's not alternating, so we can't apply the alternating series test, so we should look at doing an absolute test. So let's look at summation n equals 1 to infinity, absolute value of an. So we have summation n equals 1 to infinity, absolute value of sine n times root of n squared plus 1 divided by n cubed minus n plus 2. And this is equal to summation n equals 1 to infinity, absolute value of sine n. All the other terms are positive, so we don't need the absolute value. Root of n squared plus 1, this is positive, divided by n cubed minus n plus 2. Now, we know that absolute value of sine n is less than or equal to 1 for all n. And that's because sine x is always between 1 and negative 1. All right, so we can write summation n equals 1 to infinity, absolute value of sine n times root of n squared plus 1 divided by n cubed minus n plus 2 is less than summation n equals 1 to infinity. Sine n is less than 1, so I'll put 1 here, times root of n squared plus 1 divided by n cubed minus n plus 2. So that's because absolute value of sine n is less than 1. That's how we're able to form this inequality. So we just have to check this series on the right-hand side. If we can prove that this series converges, then by the basic comparison test, the series on the left will also converge. So let's check summation n equals 1 to infinity, root of n squared plus 1 divided by n cubed minus n plus 2. Now, if you want to know how a series behaves, basically, you look at large values of n as n approaches infinity. So for large values of n, this plus 1 is not going to affect the magnitude of this term. So the numerator is approximately root of n squared. And the dominant term in the denominator is n cubed. If we simplify this, we get n divided by n cubed. And simplify further, n divided by n cubed, that's 1 over n squared for large n. So that leads us to applying the limit comparison test. So we have summation n equals 1 to infinity, root of n squared plus 1 divided by n cubed minus n plus 2. For large n, this series behaves like summation 1 over n squared. N equals 1 to infinity for large n. So we're going to apply the limit comparison test with Bn is equal to 1 over n squared and An is equal to root of n squared plus 1 divided by n cubed minus n plus 2, and we're applying the limit comparison test. So let me write it in full, limit comparison test. So for the limit comparison test, we form the ratio limit n approaches infinity of an divided by b sub n. This is equal to limit as n approaches infinity, root of n squared plus 1 divided by n cubed minus n plus 2. Let me just write this a little bit better. Divided by n cubed minus n plus 2 divided by 1 over n squared. So we reciprocate 1 over n squared. We get limit as n approaches infinity, root of n squared plus 1, and flip this part here, multiply by n squared divided by 1 times n squared divided by n cubed minus n plus 2. Now to find this limit, we have to divide by the dominant term in the denominator, which is n cubed. So this is equal to limit n approaches infinity. So let's write the denominator, n cubed minus n plus 2. Let's divide every term by the dominant term in the denominator. Divide by n cubed. Divide by n cubed. And divide by n cubed. The numerator will be a little bit trickier. So we got root of n squared plus 1 times n squared. Now, I'm going to divide n squared by n squared, and now we have to divide by n so that we're multiplying numerator and denominator by n cubed. But to go inside a radical, we have to divide by n squared, because square root of n squared is equal to n. So divide by n squared, divide by n squared. Again, dividing by n squared inside a radical is equivalent to dividing by n outside a radical. So now we simplify. We get limit n approaches infinity, root of n squared divided by n squared, that's 1 plus 1 over n squared, times n squared divided by n squared, this is just 1, divided by 1 minus 1 over n squared, plus 2 over n cubed. So let's evaluate this limit. We have limit as n approaches infinity of an divided by bn. We're applying limit comparison test. This is equal to limit as n approaches infinity, root of 1 plus 1 over n squared, divided by 1 minus 1 over n squared, plus 2 over n cubed. Now all these limits are going to go to 0. 1 over n squared goes to 0. As n goes to infinity, 1 over n squared here also goes to 0. And 2 over n cubed also goes to 0. So the result is 1. 1 is greater than 0. That means we have a finite limit. So since the limit as n approaches infinity of an divided by bn is equal to 1, larger than 0, exists, is finite, and summation bn, n equals 1 to infinity, is equal to summation n equals 1 to infinity 1 over n squared, is a convergent p-series with p equals 2, convergent p-series with p equals 2 greater than 1. This series, summation n equals 1 to infinity root of n squared plus 1 divided by n cubed minus n plus 2 also converges by the limit comparison test. Converges by the limit comparison test. Limit comparison test. And since summation n equals 1 to infinity, absolute value of sine n, root of n squared plus 1, divided by n cubed minus n plus 2 is less than or equal to summation n equals 1 to infinity root of n squared plus 1 divided by n cubed minus n plus 2, and we prove that this series on the right converges by the limit comparison test. So by the basic comparison test, the series on the left is going to converge as well. That's what we're going to show. So by basic comparison test, basic comparison test, summation n equals 1 to infinity, absolute value of sine n times root of n squared plus 1 divided by n cubed minus n plus 2 also converges. So the original series, summation n equals 1 to infinity sine n times root of n squared plus 1 divided by n cubed minus n plus 2 converges absolutely. It is absolutely convergent. Converges absolutely. And is a convergent series. Because if a series converges absolutely, it would be convergent. And is a convergent series. This was a rather difficult example because we applied 3 different convergence tests. We applied absolute convergence, we applied limit comparison test, and we also applied basic comparison test all in the same question. All right, let's look at another example. Here we have summation n equals 1 to infinity negative 1 to the power of n divided by log of n plus 1. So recall that log x is less than kx to the p for k positive, p positive, and x large. So we know that log of n plus 1 is less than n plus 1. Now let's reciprocate both sides. We get 1 divided by log of n plus 1 is larger than 1 divided by n plus 1. So let's do an absolute test. We have summation n equals 1 to infinity, absolute value of minus 1 to the power of n divided by log of n plus 1. The absolute value gets rid of the negative sign, so we have summation n equals 1 to infinity, 1 over log of n plus 1, and we showed earlier that every term of this series is larger than every term of this series, n equals 1 to infinity, 1 divided by n plus 1. We show that in this step here. All right, so now notice that summation n equals 1 to infinity, let me write that better, this is n plus 1, summation 1 over n plus 1 is a divergent series because it can be compared by limit comparison test to another series, summation n equals 1 to infinity, 1 over n, which is a divergent harmonic series. Divergent harmonic series. Also, of course, is a p-series as well. Harmonic series with p equals to 1. So we know that this is divergent, summation n equals 1 to infinity, 1 divided by n plus 1, and every term of the series on the left is larger than every term of the series on the right, so by basic comparison test, the series is going to diverge as well, the series on the left. So summation n equals 1 to infinity, 1 divided by log of n plus 1 also diverges by the basic comparison test. By the basic comparison test. So the given series, summation n equals 1 to infinity, minus 1 to the n, divided by log of n plus 1, does not converge absolutely because we did an absolute test. We took the absolute value of every term and looked at the series, and it was essentially a divergent series. So it does not converge absolutely. However, let's apply the altering series test because it is an altering series, and let's see if it converges according to the altering series test. So we have summation n equals 1 to infinity minus 1 to the power of n divided by log of n plus 1. Why do we apply the alternate series test? Is because we see that that is basically alternating. We have this factor -1 to the power of n in the front. So let's check the conditions for the alternate series test. Number one, are the terms decreasing in magnitude? an plus 1 is less than a sub n. So we have 1 divided by log of n plus 2. Is this less than 1 divided by log of n plus 1? Well, that's true because we're making the denominator larger. That means the ratio becomes smaller. So this condition is satisfied. The first condition, that the terms are decreasing in magnitude, is satisfied. Number two, what about the limit as n approaches infinity of an is equal to 0? So taking the limit as n approaches infinity of 1 divided by log of n plus 1, this limit will be equal to 0 because we have a constant divided by log of n plus 1 that grows to infinity. The ratio approaches 0. The second condition also is satisfied. Since both conditions of the alternate series test are satisfied, this series converges by the alternate series test. So summation n equals 1 to infinity, -1 to the power of n, divided by log of n plus 1, converges by the alternate series test. But the given series does not converge absolutely. When we took the absolute value of this series, absolute value of -1 to the power of n, divided by log of n plus 1, and we take the absolute value, we got n equals 1 to infinity. Absolute value gets rid of the negative signs, 1 over log of n plus 1. And we show that this is larger than summation n equals 1 to infinity, 1 over n plus 1. And since this diverges by basic comparison test, this series also diverges. So it diverges by the absolute test. But it converges by the alternate series test. That means it is conditionally convergent. Diverges by absolute test. So the given series is conditionally convergent. N equals 1 to infinity, -1 to the power of n, divided by log of n plus 1, is conditionally convergent. All right, thanks.